Hi, in previous parts of this digital logic tutorial design series, we've taken a look at basic digital logic gates, all you need to know about those, and digital boolean logic and De Morgan's theorems, and then we switched over to designing combinatorial logic circuits, and we went through all the commutative laws and the associative laws, distributive laws, and stuff like that. So I'll link in those videos if you haven't seen it. In that video, I promised I'd show you a way to actually do digital logic reduction not using any algebra at all, but using a visual method called Karnaugh Maps. Let's take a look at it. It's pretty magical. Let's say we've got our truth table of our logic function that we want here, okay? We've got 3 inputs here, A, B, and C, and we've got 1 output we'll call X. And of course, with 3 inputs, that gives us 8 different binary states that we can have on the input. So we potentially have 8 different output functions here, and we can write this as an algebraic expression. Pretty easy. We can use sum of products. As we learned in the previous video, sum of products is we find all of the ones here on our output, and then we write that as a product expression because it's a sum of products, okay? So the product expression here is not A, like this, because it's a 0, and 1B is a 1, so we just call it B, and C is a 0, so that is not C, like that. And we've got more than one on the output here, so we have to sum the different products. So we do the products of the other one that we've got here, which is A, like that, and B is a 1, so it's just B, and C is a 0 here, so that is not C, like that. And that is our expression. So X equals that. So that's our algebraic logic expression for that function. But we want to simplify this, because if you try and implement that with just discrete gates, you'll find, yeah, you can do it, but you'll end up with too many gates. Now, of course, we can solve this algebraically, but who likes solving algebra equations? Yeah, nah. But let's do it anyway, okay? So this we find that B is the same here, okay? So we can take out B as a separate function, and then we've got C is the same either side, or sorry, not C is the same, so we can actually take out that. So it's B and C there. So we're left with, we'll put a bracket in there like that, and we're left with not A and A. So it's not A, like that, plus A. Okay, so that is, this is algebra stuff. It doesn't matter whether you're doing mathematical algebra or digital algebra like this. The rules are the same. Now this not A plus A here, we can actually simplify that, no problems whatsoever, because not A plus A is, it's always 1. So that gives us B not C, and then 1, like that, right? Or we can put 1 in brackets like that. And because this is like and 1, well, like we could put the dots in there. Like some people like putting the dots in there like that. You don't have to. You can leave it out. It's implied that it's an and function. So if you and B not C with 1, well, that just equals B not C, like that. We've simplified this algebraic expression to just B and not C. Easy. So we can just draw that as an AND gate like that, and we could go B, and of course C is not, like that, so we need to put an inverter, and C, like that, and that's our output X. You'll notice that A, it doesn't matter what A is, we always get that output function is only dependent upon B and C. And if you don't believe me, you can do this by inspection of the table, right? Our output's 1 here, okay? It's when B and C is 1, 0. B and C here is also 1, 0. And it doesn't matter whether A is a 0 or a 1 in this case, you get a 1. So that's why A does not matter. It's you only rely upon B and C to give you the output X there. But if we implemented this function up here with gates, we'd be actually using a because a is in our expression there. So we can actually draw this original function here and see how many gates we've actually saved. So here it is, this original algebraic expression. If we just implemented that directly with gates, we would ended up with 2 3-input AND gates, an OR gate, and 3 inverters like this. And we have now actually simplified that to a 2-input AND gate and an inverter. And that's the power of not only algebraic simplification, you can do this via algebraic mathematical methods, or you can do it visually using Karnaugh Maps that I'm about to show you. But you might have noticed, the keen eye here might have noticed, oh Dave, look, all you didn't need this extra inverter in here. You could have actually connected that directly up to there. And if you spotted that, bonus internet points. But these sort of circuit simplifications here are the entire point of doing Karnaugh Maps and also algebraic logic like this, and algebraic simplification as well. And this, you might think, oh, who designs with discrete logic chips anymore? No one, right? Well, no, you do inside FPGAs and inside ASIC chips and inside processors and things like that. You don't want to be implementing this many gates if you can get away with just this, because not only do you have the extra gates in the extra silicon, you also have the extra propagation delay time to get every stage of gate you go through increases your propagation delay. That slows down the maximum frequency of your chip, like your latest Intel processor or whatever it is. So you definitely want to be simplifying logic. So there is still a huge place for learning this sort of stuff. So this clever dude called Maurice Karnaugh, he figured out in the 1960s, I think, that you can actually do this visually, this simplification visually, without any algebraic skills whatsoever. All right, so what we're going to do now is we're going to draw a table that has the same number of squares as elements in our truth table. So we've got 3 inputs for our truth table, so that's 8 inputs over here. So we need a map of 8 inputs like this, and I'll put a line there, and you can draw this in any orientation. It can be like 2 across by 4 down, 4 across by 2 down. It doesn't actually matter. And now we're going to map our input variables on here. So A, B on 1, C. Once again, they could be, it doesn't matter what orientation, it could be A and C and B and C. It doesn't matter. As long as you map the correct information over here to the correct part of the Karnaugh map here. And this is called a Karnaugh map. So because of our inputs, okay, we need our C can be a 0 or a 1, just like over in our truth table, and our A and B can be a 0 and a 1. And then we just number these differently like this for all of the possible states. Now, if you had a keen eye, you would have noticed something that you might think I got wrong, but I didn't. And this is a key part of Karnaugh Maps. I numbered these 0, 0, 0, 1, 1, 1, and then 1, 0. Huh? That's not how you count in binary. That's right. We're counting in gray code. And this is one of the tricks to how a Karnaugh map works to actually simplify the Boolean expression. And you don't have to do it in gray code order like this, but if you don't, the Karnaugh map technically still works, but you won't get the most optimized, simplified solution. So I'll show you a bigger 4x4 Karnaugh map in a minute. But Karnaugh maps can be basically, they can be like 2x4 like this. They can even be 2x2, but what's the point? They can be 8x8, 16x16, etc. But once they get too big, then you start going, well, okay, it's a bit unwieldy to do this kind of thing on paper, and you might let a computer or simulator do it for you. But anyway, so what we do now is transfer all of these output data and map them into here. So A, B, and C is 0, 0, 0. So A, B, and C is 0, 0, 0. So we've got a 0 here. So that means we're going to put a 0 in there like that. But I won't bore you with the details. I'll go through and map all of these 8 lines from our truth table over to here. And there it is there. And trust me, you can go and check for yourself that this truth table equals this Karnaugh map. And this is one of the areas where you might potentially make a mistake if you're doing Karnaugh maps. You don't map it over correctly. You just double check. So if you're not familiar with the concept of grey code, it's not something that I'll particularly go into here. I might do a separate video on it. But a grey code is where only one bit changes at a time. So from 00 to 01 and from 01 to 11 like this. Because if we went 10, then we would have had this one changing and this one changing as well. And that's not how grey code works. Grey code works by only one bit changing at a time. And this has advantages in things like mechanical contactors. So if you've got like multiple wipes on a big mechanical switch and you're trying to decode the position of a switch, you would typically use grey code to prevent like multiple race conditions and stuff like that. There's some other reasons you might use grey code as well, but in this particular case only one bit changes at a time, and that's going to really help us with our Karnaugh map optimization. And you'll see over here we have some rules. It's not as bad as it looks. Once you've done these Karnaugh maps once or twice, it's easy peasy lemon squeezy, okay? But the whole idea of Karnaugh maps is that we want to group together our ones inside the Karnaugh map like this. Now this is a really simple Karnaugh map. We've only happen to have 2 ones. So what we can do is we group our ones together like this, okay? Now you can only group ones in groups of 2, in groups of 4, groups of 8 or 16, etc. You can't do 3s. So if we had like a 1 here like this, we can't group 3 ones like that. It doesn't work. You would have to group the 2 ones like that and then the 2 ones again like this. Like I just showed, rule number 2 here is the groups can overlap. You can overlap them as many and in any order that you like. Now, the third rule is that every one must be grouped. So if you've got like a 1 over here on its lonesome, then you would have to just group it as just on its own as a 1. And we'll see why that's not very advantageous later, but you have to group all of your ones. In Karnaugh maps, you ignore all zeros. You just completely ignore them because we're dealing with sums of products. So zeros aren't, you just ignore them at all. The whole idea is to group ones. You'll see why in a minute. Fourth rule here is you can only group vertically like this, or if this was a 1, you could group 2 horizontally like that, or if you had a bigger Karnaugh map with like 4 of them like this, you could group all 4 like that. So horizontally, vertically, but also wrapping. Now here's one of the magical bits of Karnaugh maps. You can imagine you can fold this Karnaugh map over into a 3-dimensional shape. You can even do it into a cylinder like top to bottom so that this wraps around to this, or this side wraps around to this side, for example, or you can actually wrap the whole thing into what looks like a torus. You don't have to visualize it that much. It's not that important, but the fact is you could wrap them. So if we actually had a 1 here and a 1 here, we could actually group them like this. You actually draw it like that. Now the 5th rule here is that you want to use the largest groups possible, okay? So if you see a group of 4 ones together, don't just do like, if this was a 1 and this was a 1, don't do 2 separate groups of 1 like that, because it'll work. It'll still work, your logic will still come out correct, but it won't be the most optimized solution. The way you get the most optimized solution, like we saw here, just like over here, we want the most optimized solution like this, and we do that by grouping together the largest number of ones. I won't go into details about how mathematically how this works, because that's like really quite complicated. You can go down the rabbit hole, but Karnaugh maps are brilliant. They work if you group them into the largest possible groups of 1. But you've got to make sure every one is in a group, even if this is a 1 and it's on its lonesome, you have to account for it. And you want to, of course, use the least number of groups, because every time you do a circle like this, every time you group ones, that actually will end up being a plus term like B, C, something like this. So let's say we had like 3 groups of 1s in there like that. We would actually, this is not probably correct, I'm just drawing random letters, but we would actually have 3 product terms in there if we have 3 circles. So each circle is a product term, and then this is the sum of products. So it's sum plus sum of a product. like this. Got it? So you want to minimize your number of groups, otherwise your expression ends up being bigger than it needs to be. But it'll still be correct. You can goof up Karnaugh Maps and do it non-optimally, but you'll just end up with a bigger expression. Not optimized. Don't want that. The whole idea is optimization. Now, here's how we solve our Karnaugh Map. As I said, this is a very simple one. It's only got that one grouped term, that one product term. So x here is going to be equal to just one term. So the first thing you need to learn about Karnaugh Maps is grouping ones together in the most optimized way possible. The second and final part of solving a Karnaugh Map is to find which inputs are dependent. What this means is that we've grouped these two ones, okay? Now we solve each loop, each grouping separately, okay? Each product term. So which of these inputs, A, B, and C, is it dependent upon? Well, it's dependent upon C because C doesn't change at all, okay? But A and B, these have different values, so you look for the input that doesn't change. Remember, the one that doesn't change. And is it A? A goes from a 0 to a 1 here. Well, that changes. It's not dependent on A, but it is dependent on B, because B is a 1 and a 1. And likewise, C hasn't changed and B hasn't changed. So bingo, we've only got our two inputs. So our B input is a 1, so we write down B like that. And then it's and. You can put the dot in here or not. It doesn't matter. Some people like to have it just to, you know, for sanity's sake, but it means and C, but C's a 0. So you go not C like that. Aha! You notice something? That is exactly the same as that. Bingo! We've solved this equation up here that was complex before. We've solved it visually using Karnaugh Maps. And because we've only got one circle in there, one group in, there's only one product term, and it's B and not C. Easy. Easy peasy. I told you, Karnaugh Maps are brilliant. You don't have to solve any algebraic equations at all. And even though this is quite a simple one, they can actually get quite complex the bigger, you know, it gets. So, and you can easily make a mistake doing this. And granted, you can make mistakes doing Karnaugh Maps too. There's two ways to make a mistake in Karnaugh Maps. One is mapping from there to there. And the other one is then mapping your groupings like this down to your sum of products terms plus, you know, C, D, or whatever it is down here. But I love Karnaugh Maps. I just love the elegant simplicity of this. And if you do Karnaugh Maps right, using the grey code, like I said here, and also you map it, and you figure out all the ones, the largest number of ones, like the largest groups, and the least number of groups, you will always end up with the most optimized algebraic solution for your truth table. Brilliant, huh? Let's just run through another example. In this case, we've got 4 terms. I haven't redrawn a truth table here, but anyway, we would have 16 elements down here because we'd have A, B, C, and D here, okay? Once again, we've got our grey code along here and our grey code down here like this. As I said, it doesn't have to be grey code, but if you don't use grey code, you don't get the optimized solution. So how can we group the ones here? Well, we can't do 3 like this, unfortunately. So the obvious one is 1, 1, 1, 1, 1, 1, 1, 1. So let's solve this, okay? X equals. Now, because we've got 4 grouped terms here, we know we're going to have 4 products. So it'll be product 1 plus product 2 plus product 3 plus product 4. So we're going to have 4 products with the sum of those in our X term, okay? So let's start with this group up here. It doesn't matter which order you do them in. The logic expression comes out, the products will be in different order, but that doesn't matter for your logical expression. Still exactly the same, okay? So you'll note, well, let's go, right? Because it's vertical like this, it means that A and B could change, but which one is not changing? Well, A is not changing, okay? So we know that it's dependent upon A. Our output is dependent upon the one that does not change here. So B's changing from a 0 to a 1, so B gets eliminated from the equation. But C and D here, because it's a vertical grouping like that, C and D don't change at all. So, but C's a 0, so it's not C, and then D's a 1 up here, so it's D like that. So we've finished our first product term, so it's a sum of products. So plus here, let's work on this one here. Which does A and B? No, A and B doesn't change, but A is a 0, so that's a not A, and B, because B is a 1, and then which one doesn't change out of C and D here? C is the one that doesn't change, and because it's a 1, it has to get included, but D changes from a 1 to a 0 in this group, so it gets eliminated from our equation. So that's our second product term. So we go plus, let's do this one down here. A doesn't change, B changes, so it gets eliminated, and this one here, C is a 1 and D is a 0, so it goes like that. And our last grouping down here, A doesn't change, so it's A, and it's not B because B is a 0 there, and not C, like that. Bingo. So there is our optimized expression. This is as optimized as it gets for this particular table. But there is more than one way to solve this. We won't simplify it any further, but we can actually group these in different ways. So instead of grouping these like this, let's group them slightly differently, okay? We could group, for example, this one here with this one down here. Remember, we can do the wrapping thing. We can group that one with this one over here like this. And then we could group these two like that. So what equation do we end up with down here? Well, let's do this one up the top here. Okay, so A, and it wraps around like this, okay? It looks like B's not changing, okay, between there and there. B's a 0, so we've got not B, A changes, so it gets eliminated, and then C and D. Not C, like that, and D. And I'll go through the rest of them. Let's do this one here. Not A, B, and D, like that. Okay, so it's slightly changed. This one over here, B doesn't change, and C doesn't change, and D doesn't change, but it's a not because it's a 0. And last of all, this one down here and here. We've got A like that, and not B, and looks like not D. Like that. I think I've got that correct. You can double check that down below. But these two expressions are absolutely identical. Even though they've got different terms in them, it just depends on how you group these ones. But you notice that both of these expressions have 4 product terms like this, and they've both got the same number of inputs. They've got 3, 3, 3, 3, 3, like that, etc. So neither of those is reducing the number of gates that you need to actually produce this logic output. That's the whole idea of Karnaugh Maps. We're minimizing the number, minimizing the size of our Boolean expression, which means the number of sums like this, and also the number of terms inside each product like that as well. But they're both the same, they're just organized differently. But these, if you implement the logic gates with these, it'll be exactly the same. Another quick example of a 4x4. I won't go on to an 8x8, but it works exactly the same way. I've just, once again, it doesn't match this truth table over here, so just ignore that truth. Can't put my hand over it. Doesn't work that way. So what is the largest group that we can actually make here? Well, obviously, it's a 4x4. Bingo. And if we had if these two were ones like this, we couldn't group 6 of them. Remember, it's got to be a single or a multiple of 2s. But we could actually have 2 groups of 4 overlapped like that. But let's go back to the original here. Now, we've got 2 1s lying out here like this. Well, we can actually group the 2 1s overlapping like that. But remember, every single one must be grouped in here. So this one, we can't go diagonally like that. You can't do it. You can't wrap around to either of the sides or anything. So that one's out there on its lonesome, and you'll see the penalty that we pay for that. There's nothing we can do about it. Like, we can't do anything. That's just, you'll see what happens. So let's take our group of 4 like this. Which one, A and B, which one doesn't change? Which is it dependent upon? X equals B, like that, and X equals D. So it's just B and D plus, because we've got 3 groupings, we're going to have 3 sum terms here. So let's do this one down here like this. Which one is it dependent upon? It's dependent upon A, like that, and C and D. A, C, D, like that. And then we've got to do OR, we've got to do the sum again. Now, this one over here on its own, here's the penalty we pay for only grouping the one like this, A and B. It's got, so A and B, it's dependent upon that because A and B doesn't change, but they're both nots. And then C and D. So C is a 1 and D is a 0, like that. So there's our final term. That is our optimized term like that. And you'll notice that we've got 2 here, 3 here, and 4 product terms in there like that. And that was related to how many ones we circled. You'll notice that because we grouped 4 together like this, we eliminated 2 of the terms. So we only end up with 2 dependent terms. This one here is only a group of 2, so we ended up with 3 dependent terms there. That's why we ended up with 3 terms in our product there. And this one, out on its lonesome, the penalty we pay is that you have to group in 4 terms like that. So you need extra AND gates. You need a 4-input AND gate, a 4-input AND gate, a 3-input AND gate, and a 2-input AND gate like this. This is why you want to maximize the number of ones like that. Because if you can group 8 ones, oh, but let's assume it was our lucky day and we had 8 ones like this, okay? So we can group our 8 ones like that. Whoa! But we've also got 4 ones like this, but we've also got 4, instead of just doing those 2, that would have covered it. But you remember, we want to use the largest groups possible. So we can group another group of 4 like that, okay? So let's actually solve that one. You'll see that with a massive group of 8 like that, the terms C and D get eliminated entirely because both of them change in there. Okay, so C and D is eliminated, and because we've got basically a group of like a 2 group like that, it's similar to a vertical group of 2 like that, it means that only A is the only one that doesn't change. So our term is just not A, like that. Or, which is a plus, that's what or means. And we've got this term in here like this, exactly the same as before. That's a B and a D. And then we go or, and then we've got this one here, which is C and D doesn't change. So C, D, and A is completely eliminated because we did that. So that is our final expression like that. We've got a lower number of input terms here, because like the most we have is a 2-input AND gate, for example, and that's just a 1, don't even need an AND gate there, eliminated entirely because we had a group of 8. Magic. So that's Karnaugh Maps for you. I love them. They're so easy. You don't have to learn, solving algebraic equations like this. You can just do it. As long as you got, this sounds like a lot of rules, but it's not. Just do it. Do a few examples once or twice. And, it's really trivial stuff. Really, there's only 2 steps. One is mapping that to that, which is pretty easy unless you goof it up, copying across. It's easy. You've got to know your grey code, okay, like this. But as I explained, you don't actually have to do that. I could do this 1, 0 like that, and then 1, 1 like that, and 1, 0 here and 1, 1 down there. It'd still work. You can still use Karnaugh Maps to solve. You'll just end up with potentially more terms like this. In fact, we can swap these rows willy-nilly, right? We can have these in any order. As I said, this could be C and A, and this could be D and B here, and you can swap them around until the cows come home, but there's only one way that will give you the optimized solution, and that's to use the grey code encoding with 1 bit changing at a time. And you can go into the complex math of why that's the case, but the grey code is the key to the optimization. It'll still work without it, but yeah, you'll just get extra terms and you're using more gates. No one wants to use more gates. Last thing we want in the world is more gates. Anyway, I hope you enjoyed that look at Karnaugh Maps. They're really great. I've always loved Karnaugh Maps. I just love the elegant simplicity of it. It was brilliant how it just, as long as you do the maximum number of groups in here, you'll always end up with the most optimized algebraic solution possible, and hence the least number of gates. Fantastic. Anyway, hope you found it interesting and found it useful. If you did, please give it a big thumbs up. As always, discuss down below. Catch you next time.